We've talked about point charges so far, but we don't just have to have point charges. We can have a continuous region that has a distribution of charge within it. And that charge distribution can uniformly fill the region, or it can be position dependent. It's like a density of charges in the region. And there are a few different ways that this can exist. You can have a line charge, which is one-dimensional, and it might look like something like a charged thin string or something like that, or just a line of charges. And that one is going to be in coulombs per meter. You can also have a surface charge, which is two-dimensional and would be in coulombs per meter squared. Or you could have a volume charge, which is 3D and would be in coulombs per meter cubed. A surface charge might be a thin charged sheet, or like an area that the charges are stuck to. Think about the surface of a balloon after you rub some wool on it. A volume charge would be a whole volume, like a ball or a cube or something like that, that is filled with charge. Now we use the symbol rho, which is spelled R-H-O, but is written rho like that, to denote a charge density. It also has some other things, so other possible meanings at different times. So when we're talking about charge density, we talk about rho L for a line charge, rho S for a surface charge, and rho V for a volume charge. It's important to note that rho, the Greek letter, is not the same as the letter P, and it is not written the same. You write the letter P by making a straight line down and then adding a bubble to it, and you write the letter rho by using one continuous line. So, we've talked about charge as a quantity, Q. What is the amount of charge in a charge distribution? To think about that, we need to think about a differential charge element in a charge distribution. Say we have a line charge density, rho L. If we select some segment of that line charge density with length dl, then the differential charge element associated with that tells us how much charge is in that differential length. And that differential length is rho L times dl. Now, rho L might be a function of position. So it is rho L at this location, which might be different from its value at this location or at this location. In the same way, if we have a surface charge density, rho S, and that can also be a function of position. So let's say that this is in the XY plane, but it doesn't have to be. And we want to know how much charge is in this little differential area, that location, which is going to be X prime, Y prime. Then dq of X prime, Y prime, like that, is equal to rho S of X prime, Y prime times the differential area. Again, in the same way, let's say we've got a volume. I'm drawing a cube because I'm best at drawing a cube. I'm not an excellent sketch artist or anything. And I want to know how much charge is in this differential volume element at position R prime. then the amount of charge that is inside that little differential volume, dq, is going to be the volume charge density at that position r prime times the differential volume element. And we can find the total charge in any volume by integrating over the line or surface or volume that that charge distribution exists on. It's really important to notice that the charge density can be non-uniform. So the result of doing this integral is usually not the same as multiplying by the total length or area or volume of the region. Because if your density varies with position, then you don't get the same result by just multiplying by the total volume or the total area or something. You have to actually evaluate that integral as a function of position. Since we can have a charge density and a charge distribution, charges are the sources of electric fields. So that means that there can be an electric field due to a charge distribution. Essentially what just happens is we turn that sum into an integral of the differential electric field contributions of each of our differential charge elements, dq's. The way that this looks is that the electric field due to some charge, some point charge I, if we were doing the sum, is going to be q sub I divided by 4 pi epsilon naught r sub I squared times the unit vector a hat I. Now that becomes a differential electric field element, still a vector, which is going to be dq, the differential charge element, divided by 4 pi epsilon naught r squared times a hat r. Now these are functions of position. So those change as you sweep your variables of integration over the source region that contains your charge distribution. But by representing your electric field this way, you can integrate the contributions from all of the differential field intensity parts. So the total electric field is going to be the integral of dE, which you can write as the integral dq a hat r over 4 pi epsilon naught r squared, like that. And then we're going to put in an actual value for big R. So we've got dq still. And remember that big R, the vector, is the observation point R minus R prime, where R prime sweeps over the source region where your charge distribution actually is. So dq divided by 4 pi epsilon naught magnitude of R minus R prime squared. That's the amplitude part of the electric field due to this differential charge element. And this little R prime denotes where this dq element exists. Now we have to put the unit vector in, which is r minus r prime divided by the magnitude of r minus r prime. You can simplify this to be r minus r prime over, combine those two and get magnitude r minus r prime cubed. That's fine. I just like to leave this separate so that it's really clear that it is a unit vector right there. Now r prime is a variable inside this integral, and it sweeps over the whole region where your charges exist. So if we're drawing a diagram of what is happening in this region, let's say in this integral we have some region that has a charge density in it. And we've got some observation point all the way over here that we want to know the electric field value at. And down here in the bottom left, that's the origin. So my value of r, whoops, I got to move that point over a little bit, is this red vector. That's r. The value of r prime has to sweep over the whole source region and select little differential elements out of that source region. And all of those get added together in the integral. So r prime sweeps over the source region. So that means that you have to integrate an expression that is a vector. How do you integrate a vector expression? There's one key thing to notice here that is really important when you're evaluating an integral that contains a vector expression. Cartesian unit vectors are constant. They don't change with position. So those are your x hat, y hat, and z hat. Or if you use the notation with the little a's, that's a hat x, a hat y, and a hat z. Those are constant. They don't depend on position. So they can go outside the integral. If you do that, that's very happy. Super easy to do. That's step one. Step two. What if you have spherical or cylindrical coordinate system unit vectors? They vary with position. If you aren't sure about that, just think about what direction does the radius vector, like a hat r or a hat rho if you're in cylindrical coordinates, what direction does it point if you're on the opposite side of the origin? It points in the opposite direction. So clearly that depends on position. How do you do this? You convert them to Cartesian coordinates, unit vectors, and then do step one. The third trick, and this one is my favorite. In general, if you can do this, you should always do it, and really you should always do it first. The third trick for evaluating an integral with vector quantities in it is to eliminate components that cancel due to symmetry. Usually you just have to draw a diagram to figure out how to do that. But if you draw yourself a picture of the problem, like say for instance, let's say we have a finite length line charge. It's got some length L. And we want to know what its electric field distribution is just on this axis or on this plane. You can tell that if you choose a differential length element on this side, it's going to contribute an electric field that points in that direction. And if you choose a differential length element on the opposite side of that center point, it's going to produce an electric field element that points in that direction, which means that the vertical or downward components of those electric fields are going to cancel. The total field is going to be purely radial. That's an example of a symmetry argument that you might make. There are a lot of different symmetry arguments for a lot of different types of problems, and problems that have symmetry arguments in them are usually the only ones that can be solved in closed form if they are at all complicated. So here's the thing. There are well-known solutions that exist to most electrostatic charge distribution problems, and they can be solved in closed form, and you don't even have to solve them in closed form because you can look up the answers. So why solve these? Furthermore, there are computer programs that can solve all the other problems numerically. So you really don't ever have to do an electrostatic charge distribution electric field solving problem ever. Why should you bother with this? The reason to know this stuff, to know how to do it by hand, to understand how the electric field due to a point charge or due to a charge distribution is related to that charge, is so that you will have the insight, the intuition, in order to be able to interpret your computer solutions or do design in electromagnetic problems, so that you'll have internalized how you think fields should act. And that lets you check your work, interpret computer results, and do design. You can't run a computer simulation if you don't know what to put in the simulation to begin with. So all of these things, you need some sort of intuition. And that is why we do these problems. So while you're sitting there cranking through the integrals, try to pay attention to what exactly is happening physically. What does the total electric field's relationship look like to the charge distribution that you're looking at?